from CEA. Gael has been working at CEA for 10 years in the HPC division. During the first 7 years, he was a systems administrator. Now he has joined the HPC storage team, and he's in charge of the next storage architecture and storage clusters administration. See how great that is if you provide a bio, people learn about you. It's really great. Okay, take it away.
Working? Yes, great. Thank you for the introduction. What we can say is that I am just from 3 years on the HPC storage team. It means that I am neither a Lustre developer, neither a kernel developer. So what I want to say you is that maybe you tell me after this talk, I could make some mistake on some errors on this work. So come to the topic. The topic is about Lustre server on kernel 4.12.8. To be more accurate, it's about the Lustre server LGCFS backend, okay, on Lustre, on this kernel version, sorry. The topics. The first level, we talk about our Flash CA project. We see that the key of the work I present here. Then the hardware storage we use to do the port to Lustre to the kernel 4.12.8. The third point will be quite interesting because we are recording the performance we have with the latest Lustre LTS from one use case. We will do a quick analysis, and finally, we'll talk about the work about the Lustre build on this kernel. And of course, we will talk about the results of this version of Lustre. So, a few words about our Flash parallel file system. This project is targeted for the next year. It is for the next exascale supercomputers. And what we want in some numbers, we want a file system to 1 terabyte per second. We want to be mounted over all supercomputers. But we need something new, that we need the integration of the current file system, which is a huge file system which is owned by spin disk. And we want to add the Flash file system as a Lustre pool. The data migration between the spin pool and the Flash pool will be done by Robinhood. I have written some I/O pattern we have on this file system. Mostly we have sequential writes, but for post-processing, we will see that we have also some random read. The question that we can ask me is, okay, we need a 1 terabyte file system. Great, we will see this morning that some sites have file system to this throughput, but we have some constraint. What we have is that we have a limited space in our data center. It means that we are close to 5 racks to this file system, and we have also random read pattern, and we need wide throughput. So that's a specific CA use case. We need to test a Flash parallel file system with SSD. I have written 2 things. That's another point, but it's important. When you are build a new architecture where density is very important, you have to care about the weight, about the floor, of course. That can be a concrete problem, in fact. And you have to watch the power, of course, because SSD consume more power, more electricity. On this topic, the topic of our CEA project, we collaborate with many vendors. And come back to the topic of today, we focus on wide throughput. I insist this presentation is based on only one use case, is the wide sequential throughput. The goal when you build an architecture, you want to have the best performance. It means that you need. The goal is to optimize Lustre on a given hardware. Some key points. We are working on the Lustre build on kernel 4.12.8 on this hardware. It's FFA14KXE. You have all numbers. But what we have to remember is that the SAS backend throughput. We have a limitation here for 20 disks to 16 gigs per second. Sorry. I have written some common parameters we use to run the benchmark. That's not very new. You have common tuning. So the goal is to be close to 12 gigs. 12 gigs is the throughput of one EDR interface. What we can see on this graph, here you have the throughput of the theoretical SAS backend to 16, and so on, up to IOR. What we can say is that there is a difference, 8% between the theoretical and ext4. That's, from my point of view, acceptable. But what is a bit annoying is that we have differences between LGCFS and IOR to 19%. It's a bit high, but this number has no sense because when you have IOR, of course, you are limited through the network interface to 12 gigs. But you have still 12.5 overhead. So how can we work to understand what is going on? First of all, it's not really a bottleneck because when you run the NSF test in white, we have the limitation to 11.7 gigs. So the line is full and all is fine. When you check the load when IOR is running, the load of the OSS servers is pretty low, but you can see that CacheWebD is at 100%. Again, what is going on? CacheWebD is doing memory reclaim. Fine, okay, but go a little deeper. What we can see is I have written a small graph here that you have the running IOR here, okay, in times. And you have in red the memory fill up, okay? You can see here that we have 19 gigs memory. And we can watch here that until memory is full, we have the bandwidth to the EDR. When the memory is full, here we are stuck to 10 gigs. Again, it will be interesting to know what is going on inside Lustre. So we do a quick profiling here with a flame graph. I hope it's readable. Yeah, you have the blue panel, sorry. So you have times here, that's a perf record here. To be honest with you, it's not the perf record of an IOR run. You can see here, for experts, that here It's an OBD filter that is running, but you have the same pattern from higher. To sum up, what we can see is here you have the symbols, the function that write data on disk. And here you have all the steps to put data in memory and to flush data in memory, on disk, sorry. The main problem is that when you count the number of spin lock we have, we are close to 13% of spin lock on this same graph. So here we can see that it's too important because spin lock is a very time expensive. That's a sum up here. And during the 30%, if we haven't this page memory allocation, we can do I/O, of course. But Lustre doesn't work as it. To sum up, at this point, we can say, OK, we can conclude that we have a page cache benchmark that we can achieve 10.5 gigs to write page in page cache and to flush data from page cache to disk. That's for the specific hardware we have here again. What can we do for that? The first idea is, OK, easy way, can we bypass the page cache usage in Lustre? You can understand that that's not very simple, and we are in discussion with Intel on this point. The second one is that, OK, we can talk with kernel people to say, oh, can we do something with a page cache mechanism to optimize this behavior? We had some discussion with kernel people that told us, oh, that's a bit hard, that's a bit very tricky. OK, take another way. What we can do, the main reflection is that if you reduce the latency, we can increase the throughput. It's quite simple as a reflection, but try it. What we have chosen is to select an I/O scheduler bypass. It means we don't want to schedule I/O. What we need to do that, we need a kernel that supports this feature. This feature is released from kernel 3.13, excuse me, where you can select the non-I/O scheduler. But when we are running this test, the current kernel version was the 4.12.8 kernel version. So the reflection was, why we don't try this current version to see if there is some improvement with Lustre. Before to begin this work, stay on the XT4 part to see if we have improvement. Of course, we have improvement. To sum up, when we run the FIO XT4 benchmark, we are close to the 16 gigs per second. You tell me, oh, it's over the theoretical speed. Yes, because the theoretical speed was based on the raw spreadsheet of the disk, and we have seen that the disks we have are a little better than expected. So we are close, the value is 16.1, so it's close to 16. So begin the work to port Lustre in the kernel version. To do that, we have to split the work in two main tasks. The first one is to begin first by the LGCFS part, and the second one, it is the OSD backend, the OSD LGCFS. We can see that about myself, in LGCFS there is 34 patches with about 9,000 lines. So it's a bit huge. But to help us in this work, there is the LU 9558 that adds the support to the Lustre client on kernel up to 4.12. There is a nice job, and that helps us to do this work. So my process, again, maybe I have done bad things, but I try to build, and when I have build error, I fix, and so on and so on. That's a way. To simplify the problem, what we have done is that when features that are not critical for us, like GSS, project quota, UXT4 encryption, for example, we, to be honest with you, we've comment that, and to concentrate on the main core of the LGCFS code. How does it work? When you build a Lustre for LGCFS, you have a procedure in the make file. It's pretty simple. You copy the full UXT4 tree of your current kernel. After that, you apply all patches that are in the kernel patches directory of the Lustre version. And after that, there is a new thread in the source that has been patched to replace UXT4 by LGCFS. Of course, this thread is used after in the OSD part. Well, about the first part, we know that we have patches that exist for Red Hat, also for SUSE with the kernel 4.4. We can say that the kernel 4.4 is much closer than the 3.10 of Red Hat. So the decision was to start with the patches in kernel 4.4 and to try to do the adaptation between the 4.4 and the 4.12. The result is good news that there are 10 patches that succeeded with no modification. 10 over 34. So there is only 30 patches to modify. If you do a little map, you can say, oh, yeah, they are bad in math because there is a lack of 11 patches. In fact, the good surprise is that people has been done a huge work to integrate LGCFS feature in upstream kernel. So there were 11 patches. It means that in our kernel patches directory for the kernel 4.12, we have only 23 patches. We do final verification to do that we have all LGCFS features with the Red Hat patches. Then, okay, we think to have done the hard way, the hard part. We try to build Lustre with the OSD LGCFS. So, no surprise, we build with no modification, it failed. Okay, but as you can read it, there is only 3 major problems, only 3. There is a rename in kernel with the patch cache shift that doesn't exist. Same way for mutex locks, that's another problem, but that's a modification of structure. And that's the same from all x@etc method. So the work is not very hard, but because the kernel commits are pretty clear. When there is a modification in the structure, you can if you read the commit, you can easily find a way to do your job. So the free patches for OSD LGCFS are pretty low. We are only to 200 lines. All is fine. We run the full Lustre we built. That succeed. We format the OST. We mount in LGCFS. Great. And we mount the target. No way, there is a null pointer. In fact, we have done a crash analysis, and we have seen that there is a rename operation vector in ext4 dir operation. So to sum up, OSD scrub and OSD handler is waiting for dot iterate operation vector, and it was renamed in iterate underscore shared in the kernel. So a patch with a fix will be applied, but only on the LGCFS part. It means that we haven't fixed in OSD part. That's a choice. When we have the file system, we run some benchmarks. But what, in fact, benchmarks, you will see our benchmark, but we will say, OK, can we mount this file system on a supercomputers? It is what we have done. The file system is mounted on a test cluster. It's running with no crash from January. So that's not sufficient to prove its stability, but right now it works. So the throughput we have. OK, we have a major improvement here. OK, you will see the overhead of LGCFS. LGCFS is pretty close to ext4 in this kernel version. Again, the Lustre version we have in the CentOS 7 kernel. And remember, what we are looking for is that we need IOR close to 12. Here we have 11.7 gigs. It means all is fine. Problem with patch cache disappeared. We will see. To do that, one way is to use multi-rail. Because with multi-rail, with two interfaces, we can go up to 24 gigs, even if our backend is limited to 16 gigs. So, unfortunately, we see here that we have a limitation to 12.7 gigs, not 16. Again, where is the bottleneck? Because it's not a network problem. Is it still the patch cache or not? Again, that's the same graph as before on the LTS version. We can see here that the problem has just shifted. OK, the good news is that we can saturate with Lustre the SAS backend, which is pretty well. But when memory is full, the bandwidth decreases here. OK. One explanation to be confirmed, because it's not easy to see the instant memory bandwidth on the controller, that we can advance that we have a bottleneck on the memory bandwidth on this configuration. The conclusion. What we can say is that the patch cache mechanism has, of course, impact on Lustre performance. We have seen that if we reduce the latency, for example, in using non-I/O scheduler, we can win in throughput, of course. The next step will be, for example, to use NVMe disk, because we saw that the protocol to write and read data on NVMe disk is pretty light. But to sum up, what we can say is that on this use case, the best performance can only be achieved with a full patch cache bypass. There is still something to do on this topic. I need to add the patches on this LU, the 10942. I need to clean something in AutoConf and add define for the specific kernel, the 412.8 inside the Lustre source code. We need to add the support of feature we have disabled, of course, GSS, Project Kota, and the goal is to add the support for the next Red Hat 8 kernel. So I have finished. Have you got questions?
Questions for Gael?
Looks like great work. Do you have any sense of when you'll get those patches pushed upstream?
Right now. It depends. I can't answer because it depends on the validation that Intel has to do with this work. But we have communication with Intel that tell us that they want to have these patches in the mainstream. So patches are ready. I have only 1 or 2 days to do a good package and good fix, good patches, and I think it will be available to everybody in the master branch.
Your earlier data, that was on the vanilla CentOS 7 kernel, is that correct?
Which one?
The earliest information you had, the kernel version, that's just on the CentOS 7.3.
7.3, if I remember.
Yeah, 7.3, so the 3.x kernel. Okay. You might want to look into, there's a feature called queued spin locks that was added. The throughput of spin locks in the 4x kernel is a lot higher. That's probably one of the main reasons your page cache stuff is better. When we move to SLES 12 from SLES 11, which is about the same version jump, the spin lock behavior changes a lot, and the page caches get a lot faster for that reason. So just something to think about as a cause for this.
Okay, we don't know that, but it's a bit strange to have the same behavior between the two versions. It means that there is something to do with the latency, and maybe that can be some improvement about spin lock mechanism in the latest kernel.
Gael, you said this patch is in use for several months now on your test system. And so because it's modifying the way, well, it's not using the I/O scheduler anymore. So I was wondering, have you been testing other use cases other than write sequential to see if it has some side effects, for instance?
We have only tests. It means that on this project, we have a lot of bench to check the performance on different parts. We are running the same test, but not to 100%. It means with this configuration, we have done some IOPS numbers. Yes, but it's not very accurate right now. The goal is to have with this version all numbers we have done with the LTS version.